Hi. We continue our effort to relate random variables, regular random variables and random sets, and we want to think about expectations or integrals by a measure with respect to random sets. So first of all, let's remind ourselves that we have the probability space, omega, sigma algebra F and P. We have the real vector space with its Borel set, okay, like this. And I want to define the following space of correspondences between these two, call it L1, of all the functions that go between omega and Rd, okay? L1 to be the set of all, let's call them psi that goes from omega to Rd, okay? Such that psi is measurable. Okay, so it's basically a random variable. And okay, the expected value, the regular expectation like you do with the regular random variable of psi, okay, is finite. Okay, so this is the L1 space. Okay, so those are the all integrable correspondences in this sense, integrable in this sense, between this space and this space. Now, I want to also define, okay, so that's the first construct here. The second one will be cell 1 of X, okay, is the set of selections X out of X such that X is in L1 of omega Rd. Okay, so such that the selection is integrable in this sense. Okay, so it's the absolute value of it as a finite expectation. Okay, so cell 1 is potentially a subset of cell, but we will say that if cell 1 of X is just equal to cell of X, all of them are bounded like that, then X, the random set X, is bounded or integrably bounded. Integrably bounded. Okay, so this is some lingo. We start from these two spaces. We define any correspondence, any measurable correspondence between the two spaces to be in L1 if this expectation, okay, is finite, and this is the set of integrable selection out of X, and in some cases it may be just all of them are have a finite, absolute expectation, and then we call just a random set to be integrably bounded. Okay, so let's see what can we do with these definitions. How do we take an expectation? So let's define the following concept, which is Aumann expectation, Aumann integral. Okay, so let X be a random set. Okay, then if cell 1 of X is non-empty, because again, there is no guarantee that this one is non-empty. The cell without the 1 is non-empty, but cell 1, okay, it may be maybe empty, but let's say if it's not empty, okay, let the expected value, okay, this fancy expectation of the random set X, okay, be the set of all expectations of X, okay, which is basically the integral over omega of X dp, okay, that's okay, such that X is in cell 1 of X. And again, this definition makes sense only if this set is non-empty. Okay, so expectation of a random set is a set by itself. It's a set of a lot of expectations. Just pick all the selections, all the integrable selections, take a regular expectation of them, and collect them into a set, and that's your Aumann expectation of a random set. Okay, so first let's look at the two examples that we keep using. Okay, so if X is just equal to curly brackets around a regular variable, a random variable, then of course the expected value of the random set X will be equal to the expected value, the regular expectation, I'm not doing the fancy E here, of X, and we put a curly bracket. Why? Because there is only one selection, okay? So, and that's also true if, okay, if this expectation exists. Okay, so that's example 1. Okay, so you can see that the Aumann expectation is a generalization in that sense of a regular expectation. The next example, example 2, is the case where we have y equal to y lower, y upper. Those are two regular random variables, such that the probability of y lower less than y upper is 1. In this case, and that is shown in my paper with Francesca, 2008 paper, that the expected value, the Aumann expectation of the random set capital Y, okay, is the interval, the regular expectation of y lower, and the expectation of y upper. Okay, so it's an interval. Okay, and the reason for that happening is that every selection is a point between y lower and y upper, so the expectations there will be in between the expectation of y lower and y upper, and you can play with the way you make that selection. You can break the interval between y lower and y upper to get any point between the expected value of y lower and the expected value of y upper. Okay, and that is shown in our 2008 paper. So again, this is showing that the Aumann expectation in that regard is a certain extension of a regular expectation of a regular random variable. Thank you for watching.